All right, guys, let's continue our discussion about enzyme kinetics. Now, given the experimental observation that we discussed last time, that the observed rate of a enzyme catalyzed reaction with respect to the substrate concentration shows this hyperbolic sort of saturation type behavior. The question is, how do you explain that, right? And I point out in the context of simple chemical kinetics, that's not so easy to explain. Um, but given that we know some things we know about how enzymes are going to work, um, we can come up with a scheme that lets us get to a functional form of the dependence of the enzyme catalyzed reaction rate on the substrate concentration. And to start, what we can do is we can just think about some of the things we know about what an enzyme is going to have to do, right? Well, the sort of simplest possible way to think about it is that, well, we know it's going to have to bind the substrate, right? Okay. And we know it's going to then have to do some chemistry. And then we know that it's going to have to let go of the product, right? We know that that's sort of a minimal scheme, right? Just in sort of the big picture way in which an enzyme's going to do its thing, right? So what's the simplest distribution of species we can think of that would describe a process like that? So let's think about it. Well, we know we've got our enzyme, right? Um, and so our enzyme is going to bind to our substrate. We know that's going to be true, right? So we can imagine then that we've got like a bimolecular binding process here with K sub 1 and K minus 1 to form this enzyme substrate complex, where K1 describes that bimolecular binding reaction, and K minus 1 describes that unimolecular dissociation reaction. Okay, then we got to do some chemistry here, right? So then we have, say, K2, K minus 2, and chemistry is going to happen on the enzyme, so this enzyme product complex, right? And then we know we got to let go, right? So now the enzyme has to let go to give us this enzyme product complex, sorry, enzyme plus product, and we can have a couple of rate constants here, a unimolecular dissociation rate constant for the release of product, and then a bimolecular binding rate constant for rebinding of the product to the enzyme. All right. Now, it is completely possible to write out a fully accurate description of this process using all of that information and all those rate constants. It's a completely doable thing. Sometimes it's the right thing to do. But for most or a great many simple enzymes, writing out that full description is complete overkill. It's a complex expression, and it's excessively so, right? Many of the terms in there aren't necessary to describe the behavior of an enzyme catalyzed reaction, at least under a certain set of conditions, right? And so that set of conditions allows us, right, or I should say, if we choose the right set of conditions, it allows us to simplify the scheme pretty dramatically, right, and still get a lot of information about how this enzyme catalyzed reaction is going to work. So the analogy here is, if you think back to my description of studying bimolecular kinetics, simple bimolecular kinetics, and applying a studious choice of experimental conditions that let us do pseudo first order measurements, we can make the overall kinetic expression a lot simpler. Same kind of idea here. All right, so what kinds of things can we do to simplify this process? Well, the first set of simplifying assumptions, and I'm just going to write that out over here. Let's call it simplifying assumptions. All right, and it's not necessarily just an assumption about how things work, but an assumption about the conditions we're going to use, right? All right, so what are some of the things we could do here to make our life a little bit easier? Well, the first thing we can do is we can only work under conditions where the concentration of the substrate is much larger than the concentration of the enzyme, right? So under that set of conditions, that lets us do make a number of simplifying adjustments to the way we think about this. The second thing, I'll cover that here in just a second. The second thing that we're going to assume is that we're only going to think about the reaction or the production of the product at early times in the reaction under conditions of so-called initial rate measurement. You can think about this as kind of analogous in terms of looking at the earliest times of the reaction, like we did with that method of initial rate. Sort of the same idea. We're going to only think about the reaction at the very beginning of the process. So under these two assumptions, if the substrate concentration is much larger than the total enzyme, E0, right? Total enzyme that's in solution, and we only look at the initial rate, there's some things that therefore become true. The first is that under that set of conditions, if the substrate concentration is much larger than the total enzyme, if we only look at the beginning, the concentration of substrate is not going to change much, right? In fact, you can almost consider it to be changing kind of negligibly, right? Under those conditions, then, something that is really useful is that the concentration, we can assume the concentration, change in the concentration of the substrate with time is approximately equal to 0. Okay, that's kind of useful. All right, what else? There's something else we can do. Turns out there is. So if the concentration of substrate basically isn't changing, so we can ignore its temporal change. So S basically becomes a constant. Something else we can do is like, well, if it's large and it's more or less a constant, the other thing that's going to be true at early times in the reaction is that the concentration of the product, therefore, is going to be way, way less than concentration of substrate. Again, large substrate excess in the initial rate, the substrate's going to be there in a huge excess over the product. Okay, what does that do for us? All right, as we start to get to take terms away. Well, if the concentration of substrate is much larger than the concentration of product, that means that when we have some free enzyme that's released the product and it's now ready to bind something else, the probability that it binds this guy, right, is essentially 0, right? Because there's so much more of this, right? So in large substrate excess, where the substrate is much larger at the beginning of the reaction than concentration of product, we can neglect the ability of the enzyme to rebind the product at these early points in the reaction. We can basically ignore it. We can assume it doesn't really even happen. Helping us out in this direction is that for many, many enzymes, the affinity, the effective affinity of the enzyme for the substrate is much higher than it is for the product. What that means is we can basically then ignore that process. We can ignore the sort of recombination, the rebinding of the enzyme by the product, or with the product with the enzyme. That's kind of cool, right? That sort of helps things out a little bit, it's looking a little bit better. All right. What else can we do? Well, there's something that you may not know, but turns out to be true, is that when the following is true, which it very, very frequently is, that the rate of product release, so that K3, right? This guy here, when the rate constant, that unimolecular rate constant for product release is much bigger than the rate of doing chemistry, right? It basically becomes irrelevant. In this forward pathway, right, when K3 is much bigger than K2, in this forward direction, the only rate constant that matters under those conditions is K2, right? Essentially, K2 becomes rate limiting, right? As soon as chemistry's happened, makes product, if that is much slower than the rate of dissociation, then the rate at which product appears in free solution is essentially equivalent to the rate at which chemistry happens, right? Well, that's kind of cool, because what that means is we can ignore this guy. All right, that's cool. All right, it's getting better. All right, how about one more assumption, or assumption / generality. Another thing that's usually true is that reverse rate constant, K minus 2, the rate at which the product bound to the enzyme goes back, right? Reverses and goes back and makes the substrate again, is usually a whole lot smaller than K2, right? And that's a direct consequence of thinking about what happens, right, in the transition state, right? So if over here, we're over here at enzyme substrate and we're over here at enzyme product, right? And you think about those transition state barriers here versus here, right? That's K2, here's K minus 2 over here. This guy is usually a whole lot smaller, right? Because that transition state barrier is so much bigger, which means you can more or less ignore the rate at which the product turns back into substrate, right? In the simplest possible scheme here. So we can make that guy kind of go away. All right, now if that goes away, we don't have to think about the product turning back into substrate. And we already said we don't have to worry about the rate of the product coming off the enzyme because it's so much faster than the rate of chemistry. What that means is we can ignore that guy completely. All right? Now, under that set of simplifying assumptions, right, that allows us to rewrite that way more complex scheme to something that looks like this. Enzyme plus substrate makes the enzyme substrate complex, K1, K minus 1. And then with rate constant K sub 2 makes enzyme and product, right? That's a whole lot better, right? Many, many fewer rate constants, many fewer species. It's great, right? But what we still want, what we still need is we need an expression that lets us explain this, right? We still need to use this scheme somehow to explain this phenomenon of saturation kinetics. All right, so how do we do that? Okay, well, what does the appearance of P in this scheme depend upon, right? Think back to when we talked about transition state theory. We had a similar sort of basic layout, and we noted that the rate at which the product appears, right, with respect to time, is just going to be equal to that species that makes it, right? ES times the rate constant for its production, right? VK2, right? That's the initial setup for determining the rate at which product appears. K2 for doing chemistry and the concentration of the enzyme substrate complex we've got to work with. That's great, and that all look familiar. That looks like a simple little first order rate equation, right? But not perfect, right? Not immediately obvious how to solve that, right? We've got two variables, three really, if you count, our independent time. We've got enzyme substrate complex, product. Oof. How do you deal with that guy, right? There's another problem, which is that the enzyme substrate complex here, right, to solve that directly, we'd have to know what that concentration is. But the enzyme's in multiple forms in solution, right? There's free enzyme, there's the enzyme product complex, which we've chosen to ignore, but it really is still there. How do you measure that? There's no easy, simple, obvious way to do a measurement that would let you get it. And yet, if you can't measure it, you can't calculate or describe the rate. So the trick is we need to express the enzyme substrate concentration in terms of something we can measure. Right? All right. So the first answer to how to do this, right, and thinking about this problem came in 1913 at the hands of Lauren Michaelis, one of the first great female biochemists, Maud Minton, and some colleagues of theirs. All right. And they made one simple additional assumption to go along with this set of simplifying assumptions that I just made that got us down to this more simplified scheme. They added one more, right? And their simple additional assumption was to say, well, what if we assume that the enzyme substrate complex here is in thermodynamic equilibrium with the enzyme, the free enzyme, and the substrate, right? If that's true, if we can assume that those guys are in thermodynamic equilibrium, I could write down from that scheme something that looks like this. I could say, well, if this is in equilibrium with substrate, right, and free enzyme, the following would have to be true, that I could describe that part of that expression there, right, the first part of that expression, as like a simple binding expression, right? I could say, well, I could say concentration of the enzyme times the concentration of the substrate divided by concentration of the enzyme substrate complex. That's the same sort of equilibrium expressions we've set up before, which I know from our discussion last time about kinetic processes being at equilibrium would just be equal to the reverse rate constant divided by the forward rate constant. And I can just give that a capital K for an equilibrium constant. It's, the notation is generally use K sub S. But doesn't that just make things worse? I mean, the whole thing I was stewing about here was the fact that we have this ES complex, right? That we don't really know how to specify. It's a variable I can't really pin down. And now I've come down here and I've introduced the equilibrium constant. I've added another one. Now, in addition to ES, which I can't specify easily, I've got this free enzyme. Now what do I do? All right, well, the trick here is to use one additional piece of information you know about the system, right? It's analogous to the exact same trick we used when we talked about that reversible kinetic solution to the unimolecular rate equation. You know one more thing. What you know is that the enzyme substrate complex and the free enzyme are related to each other through the total amount of enzyme that you could measure if you were doing an experiment. E sub 0 has to be equal to the amount of free enzyme plus the amount of enzyme that's tied up in a substrate complex in this scheme where we're neglecting the other species, right? Okay. Well, that's cool then, because now I can combine these two guys and I can make some progress, right? So if we combine these in the following way, you say, well, I need to get rid of some variables in this equilibrium constant expression. I've got the same variables here, so I'm just going to solve my total enzyme for free enzyme, which is just going to be total minus the enzyme substrate complex. That's cool. I'm also going to rearrange my expression here for the enzyme substrate complex, right? So let's just rearrange that guy, multiply this baby through Ks times concentration of ES has to simply be equal to concentration of E times concentration of S. Straightforward, right? So now, that's cool. Now all I got to do is say, well, I can substitute this guy here and then just grind through some simple algebra, I do that, what I get is that K sub S times the concentration of ES is simply equal to concentration of E0 times concentration of S minus concentration of ES times the concentration of S. Once I substitute and multiply through. All right, so let's just group some terms. Concentration ES plus concentration of ES, concentration of S equals E0 concentration of S. That's pretty straightforward. We just solved this baby for concentration of ES. You'll see why in a minute. Concentration of ES, remember that was the thing we couldn't figure out how to specify. That's got to just be equal to concentration of E0, concentration of S, divided by Ks plus concentration of S. Aha! Like eureka moment here, right? Look what we've done. We've turned something we can't measure easily into a relationship expressed in terms of things we can measure, right? Remember, we're in large substrate excess. So the concentration of substrate is essentially a constant. So I know that, baby. I know that, baby. If I'm any good with a protein concentration assay and I'm good at purifying, I know this baby too. I know all three of those terms. So I can specify, if I happen to know that K sub S value, I would know what the concentration of ES was. All right, now why is that useful? Remember, back up here with our expression here about how we specify the production of product per unit time. What does it depend on? K2 and ES. I couldn't measure ES. Wait, now I can. Oh, that's cool, because now I can down here and go concentration of product with respect to time is just equal to K2 concentration of ES, which is just equal to K2 concentration of E0 concentration of S over Ks plus concentration of S. Whoa, that's amazing, right? Because now I can specify my change in the concentration of product at the time in terms of things I know how to measure, things maybe I would want to go find. But notice something. This is change of product with time. Is there anything on the right side of this equation here that's a function of time? Remember, that's a constant, that's a constant, that's a constant, that's a constant, that's a constant. At a given concentration of the substrate, those are all constants. Again, large substrate excess, early times in the reaction, assuming the rest of these assumptions hold, and we've got something that lets us specify a scheme like that. Wow, I can do Ray with the differential notation. I don't need that anymore. I can rewrite this in a simple way. I can just say that, you know, that's therefore going to be a constant. The initial rate, it would be called. All right. It's a symbol usually V sub 0. And that's going to be equal to K2 E0 concentration of S divided by Ks plus concentration of S. One other thing. What would happen at the point where every single enzyme in solution was saturated with substrate? Right? You can't put any more substrate on any more molecules of enzyme. They're just saturated. The system is basically going flat out. The free enzyme never spends a large amount of its time, right? Some, but not a lot, right? You're basically putting the substrate on as fast as you can possibly put it on. You're making product as hard as you can go. In other words, the concentration of free enzyme approaches 0. Under those conditions, all the total enzyme is more or less equivalent to the enzyme substrate complex. That would be equivalent to saying that all my E0 is the concentration at which, you know, equals, like I said, equals the enzyme substrate concentration. That's as fast as I could possibly go. right? That means I can define another parameter. I can say the maximum velocity, V max, is simply equal to K2 times the total concentration of enzyme I've got in, because that's the point at which, you know, I can flat out can't go any faster at that point, right? If I combine these two things, I can write this expression a slightly different way. I can say, the V max is therefore, or the expression would now equal V max, concentration of substrate, divided by Ks plus the concentration of the substrate. That expression now beautifully explains that curve, right? Because if V0 equals V max concentration of S divided by Ks plus concentration of S, if you look at that expression, does that kind of look familiar mathematically? Think back to your binding equation, right? What did that equal? That was like stoichiometry, concentration of ligand over dissociation constant plus concentration of ligand, right? And remember, this was a hyperbola. Okay, that's not very hyperbolic, right? So the reason that enzyme kinetics under these conditions have that saturation behavior is because you're saturating a binding site on an enzyme. That's why these curves look like this, because the mathematics of the description we came up with require it, right? Okay. This expression is also known as Michaelis-Menten equation. And along with the Gibbs equation, the relationship between free energy and equilibria, the Henderson-Hasselbalch equation, Beer's law, the simple binding equation, Hill equation. This is one you should know, right? This is a good one. Any biochemist should be able to write that down, right? Okay, great. There's only one problem. We'll come back to that in the next video.